Sorry if that's good news or bad news. I don't know, right? it is what it is, and it isn't what it isn't, I suppose. So some housekeeping stuff to start with. I fussed with the schedule yet again, but I promise you I think this is going to be the last time. My objective was to keep it so that you weren't working on an assignment while I was out of town. That way I can be available to help, and also to try and keep it so that we have an alternation of quizzes and homeworks every week. So I juggled when the next homework is due, which is now going to be October 21st. And so I switched these two things. And everything else then should continue in that alternating pattern. Let's see. Then also homework. I've gotten a lot of questions about recoding variables. And so I wanted to go over that as well as sort of the SAS starter syntax. So all of my homework stories are taken from somewhere in real life. This one is about my son's preschool. He's actually in Miss Beth's class, Miss Nancy's class. Molly's class is for the toddlers, as he calls them. And you would think that 3 versus 4 is not a very big deal. At least I did before I had a 3-year-old and then a 4-year-old. But there is a big difference between 3-year-olds and 4-year-olds. Even though age is continuous, according to the state of Iowa, you can only have 1 teacher per 8 3-year-olds, but you can have 1 teacher for 12 4-year-olds. So it matters whether you're 3 or 4 in the school as to how many bodies need to be taking care of you. And the other variable, his rotation of his favorite television shows has been Paw Patrol, PJ Masks, and Peppa Pig. So you can Google those if you're not familiar. But I don't want the theme songs in my head right now, so I'm not going to show them to you. But your task then is to take the examples that we did as part of example 3 and figure out how to use them to answer all of these questions. So I provided you with a starter syntax file, and I also, as part of the example 3 materials, provided you with the code that did all of that in one fell swoop. So just to walk you through what the starter syntax is doing. The first several lines you will see at the beginning of all of my programs, they're just trying to make your output a little bit easier to read. It's overriding defaults that shorten things or chop things up or otherwise put extraneous information. So there's no harm, no foul if you don't have that part, but I just tend to put it on everything. From there, I'm asking you to define 3 abbreviations. 1 for what your ID number is. So I'm using, I have a bunch of fake people in my homework data that I use for practice, and so I'm person 111111. My last name is 1. So there's 1 variable for that. So when you fill in your own ID, anywhere down below where it has the words my ID, starting with an ampersand and ending with a period, such as right here, it's going to take that phrase and literally fill in whatever you said here. Same thing with my homework. So I've created a name. It's going to be called homework 02, and everywhere that you see that ampersand, my HW period, it's filling in that. So it's advantageous, rather than writing the name of the data set, to use that abbreviation everywhere, because guess what? If you wanted to borrow your own code to use for homework 3, rather than changing it for every single proc that follows, you change it once up here, and the abbreviation does the work the rest of the way through. Same logic with this thing right here. This is where my file. So I have a bunch of different names for this. It's usually file save, file path, or my file are the ones that I go with. It's file save in your examples. It's my file here. So this is a place that contains whatever files you need for this assignment. And so if you save your data set to this place, then everywhere it says my file, it will put that there for you. You can also use it to save your output. So for instance, in example 3, I saved the results to an RTF file. So I'm going to steal that piece of code from example 3 and put it right here. So in order to use that, I have to change file save to the my file abbreviation. So it would be my file. And then the name of it would be whatever I want to call it. So if I were going to do this for myself, I'd be like my homework 2, and that would be what it's called. And then this is a rich text file that opens up in any Word editor in this location, so it saves your results for you. The other piece that you need to do this is the closing statement for that command, which is at the very end. There. So now all of the stuff that you need to do goes in between, and when you run the whole thing, all of your results will be saved in a nice happy file. So this part right here, after you, and so every time that you open up SAS, you have to run all of this stuff again. It doesn't remember from last time unless you physically run it. It's not stored. In terms of recoding, I'll show you how to do that. So there is a very bad example in example 3, I've come to realize, of how to do this. I have a list, I have started a file that's called Things to Fix for Next Time from my class, and that's the first thing that's going in there. Oh, by the way, I did fix your homework. Questions 15 and 16 have been swapped, so they're now correct as written in here. Thank you for catching that. Here's the example. So the way that this should work, if I'm going to recode, let's say that I need to recode classroom so that Beth is the 1 and Molly is the 0 instead. Let's do that. Recode classroom. So the first part here is make a new variable that is missing. That's what I'm doing. So I'm going to call this variable, since it's going to be about Beth, is Beth, that's her name, equals dot. Then recode if old then new. So the variable that I'm starting with, by the way, you don't have to have everything indented, it's just that I'm anal and it makes your code easier to read if it's all like aligned. So the old variable was classroom. So if the old variable was 0, the new variable is Beth, is 1. If the old variable is 1, the new variable is 0.
I messed up because I kept on doing Beth, Molly, like, come on, like, read Beth. Okay, this makes sense. So the old variable is the one that's already in
Yes.
the program rather than making it remember something.
Yes, but it's backwards in Stata. It says new is if old is that. So I can help you with that if you need.
Question.
Yeah.
When we're looking at expected, so we can do expected frequencies.
Mm-hmm.
We can't do expected, or can we do expected percentages?
I don't know that you can ask for that, but you could. It doesn't matter because the same information. You're looking at the relative difference between the obtained frequency and the expected frequency, which would be in the same direction as the difference between the obtained percentage and the expected percentage. So yeah, in the
Oh, go back one here.
oh yeah, these are percentages. Is that why you're asking?
No. Yes.
Yeah,
yes, those are. Yes.
that's another word I need to change. Yeah, these should be frequencies.
Okay. It all is clear now.
Yep, that's my bad. Thank you for asking.
Yeah.
Add that to my list. Things to fix for next time. I will fix that as soon as I can. I just have to make sure that no one's in the data set in order to go in and muck with things like that.
Sure.
So the code, by the way, to get those expected frequencies is proc freak, the magical word expected. That adds those to your list. Okay.
That last line.
The proc freak?
Classroom, classroom.
Oh, the recoding? Sure. Let me go back to that.
Classroom is one,
Mm-hmm. So classroom could just as easily be called is Molly, because that's the one. Which is why in my example I had female because female was the one, but then it gets confusing as to what's a value and what's a number, and so sorry about that. Would you like to do age group? while we're here? Why not, right? See, free homework help. So let's do the same thing. Make a new variable that is missing. I'll add one. How about we call this is 4? Because that's what 1 means. Yes, you are 4. Is 4 equals dot, semicolon. And then we'll add that to our list here. If, what do I put here?
Age group.
Yep, here's the original variable. If age group is 0, then is 4 equals, actually no, is 3, that's what I need to do, my bad. Is 4 is age group. There we go. Is 1. If age group equals 1, then is 3 equals 0. So you really only need to do one or the other of these. SAS gives you the proportion of zeros as your test. Stata gives you the proportion of ones as your test. So you just need to recode one or the other based on which software package you're using.
My ifs are red.
Then you may be missing a semicolon before.
I'm not missing a semicolon.
Okay.
No, I don't know.
Yeah, I would, yeah, let me look real quick.
Do I need to put an asterisk before it? It's just gonna look like a note.
Oh, it's because you're in open code. So that's the other catch. All of these transformations have to be within this data set combination. Otherwise, it doesn't know which data set you're trying to make new variables in.
Oh, I see.
So I just added mine inside the part where the label's before the run. But yes, good catch. Red is wrong. So if you see red, something is wrong. The other part too, if you forget your semicolons, whatever follows is going to be the wrong color. So watch what happens if I forget one here. Watch what happens to run. Okay, run is black, and it should be blue bold. So that can be diagnostic for you if the colors are off. Another thing that is diagnostic, if you forget to end a semicolon on a comment like this, then whatever follows stays green because it thinks that's part of your note to yourself. It doesn't understand. So the analogy I came up with yesterday or the day before maybe, like remember like people talking on like walkie-talkies, like come in, over, right? And they always have to say over when they're done. Just think of the semicolon as like over. Okay, does that help? Great. Any other homework questions that I can clear up while we're on the topic? It's due next week, Monday night. Yes, ma'am.
I'm gonna go over real quick. So I had a question about how, can you just roll down? It's in the drop down ones,
Mhm.
and I think it's the last one in the first column. That one, number 55. I don't understand what it's asking or how I can find it in SAS.
It is not a SAS question. It's an interpretation question. So SAS will not tell you what the numbers mean. That's your job. So do you not understand the choices?
Right. I'll just go back in my notes because I think I don't understand what the effect size is. So I probably just need to go back in my notes.
So this is referring to the answer to age group and classroom teacher. Let's see. Oh, you haven't done that yet. It's from section 2. That's why I moved that section. So that question actually refers to, if you haven't gotten down there yet, I'm asking for the correlation between, where is it?
Oh.
Age group and teacher. Where is that? Looking.
We did do age group though, and classroom teacher above, didn't we?
Okay, that's where it is then.
It's like a very
Oh, there it
big
is.
number that's negative point.
Yeah.
Yeah, so Pearson R effect size, there it is. Yeah, age group and teacher. Is that that's number 55?
Mm-hmm.
Yeah. Okay. So the answer to number 20 is the Pearson's correlation between age group and teacher. A correlation is an effect size.
Gotcha.
R more generally is an effect size. Pearson is a particular type. But so I'm just trying to be as clear as possible that I want the Pearson's correlation. And so then the question is, asking you,
It's valid.
well, yeah, this one is like, what did you find,
Mhm.
right? And then whether or not it's valid for various reasons.
Okay, I also am confused about that.
Okay.
How do we tell if it's valid or not?
That's, yeah, I was like, I just don't know. I guess I'll have to do more work.
Yeah.
Um,
And where am I, yeah, no.
So think about the type of variables that the correlation is between, and then search your notes for a discussion of caveats for correlations between those types of variables.
Okay. Because like, logistically speaking, there's not, well, never mind. Okay, I think I understand. Or I think I'm getting the hint.
And I have the same question later on about another correlation between fits thrown and favorite TV show. Same set of answers.
Oh, yeah.
Okay. Other questions? No? You're good? Yeah, you're good. Good. Good enough, I guess. Good for now. If you run into problems, don't hesitate to email me. You can send me screenshots of like if you get an error message, or you can send me snippets of code and say, why isn't this right, or why isn't this running? And I can help you troubleshoot. So you're not on your own here. Remember the 15-minute rule. If you bang your head against the same thing for 15 minutes unsuccessfully, stop and get help. All right, then I will shut that down. Shut this down. Gesundheit. And we'll go back to lecture 4. And example 4. We get to start that too. General linear models. You ready for this? All right, tell me what you remember from last time. Make sure I'm streaming. Yep. What is a general linear model for?
Predictors and outcomes.
Variables have to be either a predictor or an outcome. What kind of outcome is a general linear model supposed to predict? Something quantitative, preferably continuous, or at least continue-ish, right? Something without obvious boundaries, floor or ceiling effects. What kind of predictors can go into a general linear model? Your choices are binary, nominal, categorical, quantitative, or all of the above. All of the above, absolutely. General linear models get called special names based on what kind of predictors are in there, but it's all the same thing. So it's what do we mean by linear? What does that term mean? A line. That's a linear relationship, but the term linear and general linear model means something specific about how the model is formed. That's what general means.
Yeah, it's a linear equation.
It's a linear equation, so it's constant times variable plus constant times variable. That's what the term linear means. Currently, we are using that linear model to develop a linear relationship between, it was education and income, that we talked about so far, but you can use a linear model to develop a nonlinear relationship as well. And that's actually the next set of materials I'm working on upstairs. Good. And what if you want to predict some other kind of outcome?
Come back next semester.
That's it. Come back. That's the world of generalized linear models. So it's the same idea of putting any kind of predictor of other kinds of outcomes. And so we would pick a different distribution and have a couple other things that change to make sure that the predictions stay meaningful in those cases. So, So what we are looking at right now is predicting quantitative outcomes using the normal distribution. And here are two special cases when you only have one predictor in the model at a time. If it is a continuous or quantitative variable, that is called a linear regression. A simple linear regression if you only have one. And we're going to also see today what happens if you have a binary predictor, and that is called a t-test. Now that's kind of a stupid name because you've already used t for like 16 different things, and you'll continue to use t for lots of other things. So I'm sorry, that's just a dumb name. So we're just going to say it's a general linear model with one binary predictor. That's what it is. Okay. What is an empty model? What's another term? Empty. What's that mean? No predictors. What's it for? What does it give us?
Oh, the extra.
The extra?
The residual?
It has two parameters. There's a beta 0. Let's get to that.
Fixed intercept?
Yep. And if you don't know anything else about a person, what's your best guess for their outcome? The mean. Yeah, the most likely value. That's what beta 0 takes on if you don't have any predictors. The other parameter is the variability of the e's. What is e? Residual. It's how far off. How far off each y is from the one that's predicted by the model. So we were looking at, for instance, this slide. So empty model, for instance, for family income. So the y-axis in this picture is family income in thousands. It's the variable we've been playing with. I'm working on developing a prediction equation for one particular person, this person out here, that has education equals 8, which in this new scale of education actually means 20 years. So that's the first thing here we've talked about in terms of predictors. 0 needs to mean something. When you introduce a predictor into the model, the intercept takes on the expected outcome when the predictor is 0. So rather than making an intercept a nonsensical prediction, we want to make it something useful. So what value to center at is totally up to you. I could have picked the lowest observed value, which was education of, I think, 5 years. I could have picked the highest. Something in the middle is just customary. So I picked 12 because it's in the middle. So that's why this y-axis has 0 in the middle, because 0 means 12 years of education. We're predicting the outcome for education minus 12 equals 8. So the empty model, the mean for this outcome of income is 40, so $40,000. Relative to the predicted outcome for everybody, which is this flat line right here, this person up here is off by 115. Their income is higher than predicted by 115. If I take the E for each person, square it, sum it, and divide that sum by the sample size minus 1, that gives me the total variance in my outcome. So at this point, everybody gets the same predicted value, the mean. So 1980 is all the variability there is to be had in income. 40 is the mean. So that's like the worst we can do. Everything gets better from there. So if we add education, I now have 2 betas. So these betas, these are called fixed effects. The term fixed means everybody gets the same. So everybody gets the same beta 0 intercept to contribute to their predicted score. Everybody gets the same beta 1 that multiplies their X predictor to contribute to their score. That's why the betas don't have I's. Everything else has an I subscript because it's per person. The original outcome, Y sub I per person, E sub I per person, X sub I per person. Education. So this new equation then, I'll show you how I got these numbers. They came out of Proc GLM. Gave me a fixed intercept of 27. So if I have 12 years of education. That's when my new education variable is 0. I am predicted by this regression line here to have income of $27,000. So that's like right here. For every additional year of education, my slope right here, so slope is rise over run, right? Change in y per change in x. So this slope of 6.6 tells me that for every additional year of education as my x, my y income is predicted to be higher by $6,600. Slopes are almost always interpreted in a positive direction, but it would be equally valid to say for every year lower education, my income is lower by $6,600. So that the line you can go either way. But the intercept in the middle is the you are here sign. Everything is sort of relative to that as an anchor point.
So it will always be like I'm thinking like, what if it was smoking and for every year you smoke more, your life expectancy is 5 years less or something like that?
Yes,
So it could go this way? Or
yeah, yeah. So just like that, I gotta do this again here.
Yeah.
There we go. Negative correlation, negative relationship would be a negative slope. And in that case, as x goes up, y goes down. Smoking goes up, living goes down. Smoking goes down, living goes up. Right? So for this person, they have the highest value of education observed, 20 years, which is 8 above our centering point of 12. So I plug in an 8 for them, and they get a predicted outcome. So that's what this is called a caret, I think. It's called a hat in statistics. It's like a pointy hat, but it's a hat nonetheless.
It's really called a hat?
Yeah. Yeah, no, so I'll tell you how quant cool some quant people are. So my husband went to a conference, it's AERA, you may have gone to that. There's a satellite conference called NCME, which is like the measurement quant people. And as conference swag, they gave out a theta hat, which had a theta symbol with a caret on top on a hat.
That's amazing.
A theta hat.
Only they would understand that.
Exactly. It's one of those like jokes where like only 1 in 10 people who see will be like, that's hilarious.
If it
But
was just the Y as a hat, that would have been even funnier. Is that it's your Y hat.
yeah, it's a Y hat. Yeah. So yeah, so this idea here, this hat means what is predicted by the model. So E is not part of it. Because what that is saying is that anybody who has 8 years of education would have the same predicted Y of 80. E is an individual thing, how far off you still are after taking into account your education level. And so for this person, the red part of the deviation between the sample mean, which is what the empty model predicted, and the regression line, which is what our new model with education predicted, this is explained variability. So why is it that this person has such a high income? Well, they went to college a long time. But the blue part, that's their E, that's what's left. They're still higher than what the regression line predicts for some other reason. So E is error, is residual. You will hear both of those terms used interchangeably. I tend to like residual better because it conveys to me offness, whereas error makes it seem like something's wrong, like I screwed up somewhere. Like, no, it's just I don't know yet. I didn't screw anything up. It's unknown, unexplained. So now, if I calculate for each person what their new E is, so note the difference in the formula here. This formula part is exactly the same. E is always how far off your actual Y is from the predicted Y. What changes is what goes into predicted Y. So it's becoming customized. It started as generic, like everybody gets the same mean. Now it's custom based on education. And if we added other predictors, it would become further customized based on those. So if this new predictor matters, if beta 1 for its slope is something different than 0, then the person's E should be smaller than what it was. Now, some people's E's may get a little bit bigger, but some people's E's may get smaller. On the whole, the E's are supposed to be smaller. And that principle is the theoretical part behind where all these formulas came from. The way that you figure out what this line should be is the one that minimizes the squared residuals, that results in the smallest E on the whole. This is called ordinary least squares estimation. That's what it's called, or OLS for short.
Ordinary?
Ordinary, I wrote it up here. Ordinary least squares estimation. The term least squares refers to the numerator here. We're trying to come up with whatever predicted value results in the smallest set of E deviations for the sample. I will spare you the rest of the details about estimation. How's that sound? This is the part where we can trust people who are smarter than us to have figured this out correctly and use their work. The bad news is that these handy-dandy ready formulas are only available for general linear models. Once you get into anything more complicated, the stuff has to be found iteratively through computers. So that's why I don't bother teaching the hand calculations part of this, is because it only works for a very small subset of what you would eventually want to learn how to do. So, okay, how are we doing? Yeah? Good.
I have one question.
Yeah.
So then could you keep on, could you keep on running that to like make that explained number go less and less?
You want explained to go more
I'm sorry,
and
the
more.
unexplained?
The unexplained to go less and less, yes.
So then you're like, add the model. Like, now I'm going to control for inheritance. Now I'm going family money. And then if you get to 0, you're like, we figured out this guy. We figured out this outlier.
Yeah, you figured out everybody.
Oh, everybody.
Well, yeah, so if you get to collectively 0, right? If there's no more E's at all, then you figured out everybody. But you can't just figure out one guy. You have to try and figure out everybody simultaneously.
Okay, that helps.
Yeah. So what you could do, though, to try and figure out everybody is put in a predictor that is specific to whether or not this is Bob, right? If it's Bob, here's your effect of being Bob, and that would just fill in whatever gap is. And then here's the effect of being Susan, and that fills in this gap. And here's the effect of being Carol, and that fills in this gap. And you can keep doing that and doing that and doing that. And that's the idea of degrees of freedom. Like, how many of these parameters, points, did you have to spend to reduce your variability? And you can spend up to n, which would be the same thing as putting in an effect for each single person. Okay. Other questions? Okay, so at this point, we're just talking about interpreting what these numbers mean. I've got a 27 for my fixed intercept. I've got a 6.6 for my fixed slope. The more general umbrella term is fixed effect. So an effect can be an intercept or it can be a slope. What these betas mean is always context specific. It's always relative to what is in the model and how you set it up. But what haven't we talked about yet? What might I want to know about 6.6? Does that seem like strong to you? Does that seem good? Meh. Exactly. So we need some way of quantifying how far it is from expected, right? We need a standard error, we need some significance testing. So this is what your software will do for you. Every fixed slope that you get is going to have the following pieces of information provided for it. The estimate. That's our best guess for what the slope is given the data. So 6.6 in this case would be the estimate. Standard error goes with it. So just like we had a sample mean and a standard error of the mean, we have a sample slope and a standard error for the slope. It's an index of imprecision. Imprecision or M? M or N? N. Why am I saying M? Am I thinking of yet another word? I don't know. I should just stick to quant and leave the English behind. Imprecision. Unprecision? I don't know. Bigger is bad. How's that? More error. So it's what it sounds like. It is an index of the quality of the most likely estimate where smaller is better. Smaller means it's more precise. We're more sure that 6.6 is the best answer for what our slope could be. T-value. So if we take the estimate, divide it by the standard error, that gives us T. Now we can use the t-distribution to figure out a p-value, same as you did before. We need, in order to use the t-distribution, we need denominator degrees of freedom, which is sample size minus the total number of fixed effects. So in this example, how many fixed effects do we have? 2. Very good. We have a mean and a slope. That's what it took to make our prediction. So once we have an obtained t statistic and we have denominator degrees of freedom, that gives us a p-value. The probability that we would observe a t that big if the true t were 0, if the true slope were 0 is the idea. And we can also make a confidence interval around the slope. So if it's a 95% confidence interval, then we would use the critical value 1.96. And this describes how confident we are in that slope estimate. So it would be the range in which the true slope value would be expected 95% of the time. So this process of judging the significance of a slope by itself using its estimate and standard error is what's known as a Wald test. Because we're only testing one slope, it is called a univariate Wald test. Sometimes your software package will label this quantity of estimate divided by standard error as a z instead of a t. Question you were asking me earlier. What's your name again? Jing. I was going to say Ling, and I was close, but not quite. Jing. Okay. So you found a formula for a one-sample t-test and a one-sample z-test that were exactly the same, right? Yeah, because it's this idea of estimate divided by some index of variability. The question is, what do you then do with that result? If you needed to estimate the variability using a sample, or you're concerned about sample size, you treat the result as a t, you get your denominator degrees of freedom, and then you figure out your p. If you know the variability, or you're not concerned about having a small sample, you can treat that ratio as a z instead, and use a z distribution instead of a t distribution. T is flatter when smaller samples, so they're slightly different shapes. One nice thing that I'll mention here in terms of computing standard errors and confidence intervals, a fixed slope between two quantitative variables is an unstandardized version of a Pearson's correlation. Putting a confidence interval around a correlation is much harder because it has boundaries of plus or minus 1, whereas slopes can be anything from negative to positive infinity. So we don't have to worry about nonlinear transformation to form confidence intervals for slopes the way we do for R. So it's a much more straightforward process. So what goes into a standard error? Okay, do you remember standard error for the mean? Okay, what is a standard error for the mean?
Population versus.
How far off your sample mean is on average from the population mean. So it's like the standard deviation of your statistic. And what goes into it? You answered this question on a quiz a couple weeks ago.
Sample size.
Sample size and Variance, yeah, so basically as variance increases, you're less sure what the mean should be because the distribution is wider. And as sample size increases, you're more sure about what the mean should be because you have more data to go with. Guess what? Standard error of a slope, same idea. The numerator is variance, same as standard error of the mean. Denominator is a function of sample size. So it's sample size minus the number of parameters that you had to spend. And then last but not least, because it's the standard error of a slope, and a slope describes something in units of x and relative to units of y, we also have to know the variance of x. So the same rules apply. If there's more variability in y left over, the standard error is going to be bigger. If we have more people, the standard error gets smaller. So in the same way that you can think of the standard error of the mean as how far off your sample mean is from the population mean on average, you can think about your standard error of a slope as how far off your sample slope is from the population slope on average. Same idea. I'm giving you the formulas because I want you to have a conceptual understanding of where this stuff comes from, but no way did I do this math. I ran it through SAS and I got the numbers, and so I'll show you how to do that too. So in this analysis, it came out that the standard error for the slope is 1.35. So on average, that is the expected difference between my sample slope and the population slope. If I take my estimate, 6.6, divided by its standard error, 1.3, that works out to be 4.9. So what do you think about a t of 4.9? Without even looking it up. Is that big? Remember what t of plus or minus 2 is where the 95% mark is, right? Roughly. So 4 is like way out on the right side. It's out in unexpected territory. If the true slope were 0, we would get a slope that yields this t like really not very often, less than 0.0001% of the time is the p-value. So this would be reject or retain the null of the reject, significant. 6.6 is not 0. If I take that estimate and confidence interval, or estimate and standard error, I can make a confidence interval. It's 3.93 to 6.28. So if I redid my study over and over and over and over again, this is the interval that would contain the population slope 95% of the time. If this interval overlaps 0, that means you have a non-significant estimate. The interval is entirely on the positive side. So that is another, it's telling you the same thing, basically, that as the p-value is telling you, that this is not 0. Okay. How are we doing? Okay. So you can also calculate what the model says is a predicted outcome for any person and a standard error for that prediction. However, that standard error is a little more complicated. I have to do a demonstration here. So yet another reason it's good to come to class, right? I highly recommend when you start teaching that you get one of these, because it's just really fun to be like, wake up! You know, start jabbing at people, or it makes you feel very professorial.
They have one with the finger.
Wait, with the finger?
They have a finger one. If you
Oh,
point,
that
and
would
then
be
you
even
poke.
more fun. I once got to give a talk at a university in Switzerland, and they had one of these. It was like this huge auditorium. I swear it was like 30 pounds. It was like this big wooden stick. I was like, oh. So this, nice and lightweight, collapsible. But I'll do my slope demonstration, right? So if I tell you the slope is here, the impact of prediction changes more on the extremes than it does in the middle. Like if I make a new slope, the people in the middle stay pretty much the same predicted place, but the people on the outside are the ones that wiggle. So the further you go away from the middle, I want to say fulcrum, is that a word? Okay. Yeah, the further you go away from the middle, the more a little change in the slope creates a bigger change in the prediction. And so these standard errors around the predicted outcomes take into account how far away the x's that you're predicting for is from the mean. And it looks like this. So SAS made this plot for me. So the window of prediction around your predicted outcome is narrowest when the predictor is at its mean, and it increases as you move away from that. So this picture shows you two different types of predictions. The blue shaded area here is the range of the model predicted outcome. The dotted lines out here convey the predicted range of total scores, also taking into account how much variability is left over. So for any individual, if we take into account all the variance that we don't know, the window is way wide. If we're just talking about the window around prediction of things we know, it's very narrow. But it's narrowest in the middle. So that's not something that comes up a lot, but I thought I would mention it because one of the things that people use these models for is prediction in a new sample. So if you develop a relationship, say, between education and income and you will apply it to a different data set, just keep in mind that you'll be less certain about the predicted outcomes the further away from the mean of education you go. All right. So you want to see how I got all these magical numbers out of SAS? And Stata? Why not, right? So I've got example 4. So this is the same GSS data set we've been playing with. I think I'm going to have maybe one more set of examples with it, and then I'll switch to a different one so you don't get too bored. But I am in SAS, defining file save as where all my stuff is, and then referring to file save to pull in the data set. So this is the same subset that I created from before. Analogous process in Stata. So first thing, I am making all of the variables that aren't already made for me that I need to be able to do these models. So within SAS, any data transformations have to happen within a data set combination. So this is like save as itself. You have to start with data and then set, and then ask it to make your new variables, and close with run. So family income divided by 1,000, that's going to be the outcome. I am centering education. So centering refers to the process of either adding the same value or subtracting the same value to every case so that you change where the mean is. So in this case, what this line of code means is make me a new variable called educ12, education 12, equals from the original variable that is called just educ education minus 12. So my convention in naming variables is to put the centering constant at the end so that I always know what 0 means. So education 12 means 0 is 12 to me. I also ended up using making some z-scores to make some of my pictures, and so I include that in here, although we're not going to use them in the models. So this is not something you'll have to do very often, but I wanted to keep it in there for you. Stata code to do these things looks very much the same. The only difference is that you have the word gen in front of the new variable that you make. And no semicolon at the end. Stata does not require an over. Egen is how you make z-scores. And selecting complete cases again is the other thing I'm doing. So in addition to, where are we at here? In addition to education and family income, I'm also screening cases based on whether or not they have a variable for married, where 0 is not married and 1 is married. So we'll have a binary predictor to work with eventually too. Okay. So first thing, if I don't know anything about my data, let's figure out what the properties of it are. Descriptives. So I am writing down all of the things that I want out of these variables. The only one that is not included by default is variance, and because I added it, I have to list manually all the other things that would have been included by default. This command, no labels, just suppresses the labels, and I did that literally so I could fit this on a page. That was my only rationale. So I want to highlight a few things that we're going to see here. The mean of family income of 39.7, that's going to come back to us as the fixed intercept from our empty model. Its variance of 1980 is going to come back to us as the residual variance of the empty model. And here's some pictures of the data that we're looking at. So family income in thousands. One of the things that is often confusing to folks about general linear models using the normal distribution is whether or not a distribution that looks like this is okay. Does this look normal to you? It's like, well, some of it sort of does a little, but then there's these people, the super rich. Like, is it okay if I use a general linear model in this kind of outcome? The truth is, I don't know yet. Because it's not that the data, it's not that the outcome has to be normal. It's that the residuals do after you're done predicting. And I don't know what those residuals look like until I'm done predicting. So remember the analogy I gave you last time? It's like if you're going into a dressing room to try on something and you kind of have to like visualize what it could look like with the right accessories and the right shoes and everything. Like just think of it that way. It's like the dress doesn't have to fit perfectly off the rack, but it has to look awesome eventually after you do whatever alterations and, you know, makeup and hair and shoes and stuff. So this is education. Does education look normally distributed to you? Nope. Is that a problem? The answer is doesn't matter. It's never a problem. General linear models make no assumptions whatsoever about what kind of predictors you have. It can be whatever shape it wants. Now, what's more relevant is whether or not a linear relationship between education and income is plausible given this distribution. But that's a different question. It's not about the shape, it's about the type of association. Correlations between the two. So this is a Pearson correlation between education, centered at 12, and family income in thousands. Quick question for you. Would this correlation have been any different if I used original education or if I used original family income not in thousands? It would be the same because correlation is a standardized estimate. It corrects for differences in mean, it corrects for differences in variance. And so a correlation of 0.45 means positive, right? More education means more money. It is not 0, decidedly. We reject the null on that. Likewise, we have a correlation between income and my binary predictor. Right here. So married is 1 if you're married, and 0 if you're not married. So this one we'll talk more about later, but the idea is that the higher category still goes with higher outcomes. So if you are married, you are more likely to have a higher income. That's what positive correlation means in this context. And here's some confidence limits and all that stuff. Okay, so all of this is stuff you already know how to do. It's the first thing I would do for any data set, but now we get to the new stuff. Here we go. Your very first linear model. Isn't it exciting? Woo. By the way, this is data science. if you'd like to make yourself sound fancy. Yeah, statistics is so like passé. It's all about data science. On my Facebook feed, there's some place that's advertising that you can get a degree and a job in data science with 1 month of study. And there's all these comments from statisticians underneath saying, would you go to a neuroscientist who's been practicing for 1 month? Like, nah, but you got to start somewhere. Examples in every field, right? Yeah. So, here's SAS. By the way, this title, this is like a comment in that SAS doesn't really care what you put here. The difference is that the title shows up in your output window. So it's like your own trail of breadcrumbs to keep track of where you got your numbers from. So that's why I'm doing title as opposed to just a comment here. Proc GLM. Guess what that stands for? Yeah. So just like all the other procs, the first thing it wants to know is what data set would you like me to use for this? You tell it. This is an option name length. That just means it so it doesn't truncate your variable names if they go too long. So otherwise it has some restriction on how many characters it will start to print and it gets annoying. Model. So this statement right here is how you define what your outcome is and what your predictors are going to be. And the form of it is exactly like it looks if you were to write the model equation. Y, family income in thousands, equals, and then there's nothing here. The slash is where the options start for things that you're asking for, but the fact that there's nothing here means we're doing the empty model, no predictors. Now there is something in the equation, there's beta 0. What is that again? Fixed. More generally starts with an I. Intercept. In this case, it will be the mean. That is included by default. So it assumes you want that. If you don't want that, you have to shut it off. So you don't have to write intercept because it's already there. So that's sort of the hidden thing right here. After that are options for things you can ask for in your output. The word solution means the actual intercepts and slopes, which is not a default, crazily enough. If you want the numbers, you have to ask special for them. Alpha equals 0.05. I'm using that to define confidence intervals for the parameters. So what if I wanted a 90% interval instead of a 95%? What would I change this to? 0.1. Very good. GLM is one of the procedures in which you can have more than one model. And so even though it seems redundant, you need both of these things, run and quit. Otherwise, it just sort of hangs. This title right here, without anything following it, shuts off this title. Otherwise, it will keep printing forever and ever as you run more things. The analog in Stata is just these two words right here. Regress and the outcome. You get confidence intervals by default, and the answers come out by default.
This is for this right here is for Stata, right?
Yep.
So ignore this if I'm just sticking with SAS.
Yep. And this, by the way, is why some people love Stata. People who hate typing love Stata, because everything is just that, the bare minimum. The analog, by the way, in Stata, commas are used to separate options for things, and in SAS, options are almost separated almost always by a slash. So those are analogous. Okay. Now here is my output. Only some of this we're going to talk about today. We're going to come back to this after we learn some more stuff, but I'm trying to limit the amount of new things to talk about in one session. So I've highlighted this number right here. That's my total variation. So the empty model gives me the variation of the e's, where the e is the difference between your outcome and the mean. That's how we define variance. So that 1980 should exactly match the variance of your outcome. That's what it means. Likewise, down here, intercept. First column, estimate. Best guess for what it should be. So this is my beta 0. 39.7 is the grand mean for income. If I don't know anything else about you, that's my best guess for your prediction, the end. Standard error. That is the imprecision, I swear I want to put an M there, imprecision of this. So this is a function of how much variability we still have in the outcome, the 1980. The scale of, actually in this case it's not, there's no X yet, and the sample size. So this is basically like the standard error of the mean. Estimate of 39 divided by a standard error of 4 and some change is my t. This t of 8.7 goes with a p-value of less than 0.01, and here's the confidence interval. That is this estimate plus or minus 1.96 times that standard error. Now here's a question for you. This intercept is wildly significant. Look at how huge that t is. Do I care or do I not care?
You don't know yet?
I will say most of the time we don't care, right? Right, Michael? Why don't we care?
Because this is just if your predictor is 0.
Yeah, this is telling me that my mean for my variable is not 0. Okay, thanks. Now, when might I care? If 0 meant something. So if I centered this variable such that 0 was some sort of reference value, right? Then that would be the same idea as a one-sample t-test, comparing a mean against a population value. You can trick this to be able to do that kind of thing for you, but most of the time, the intercept is just your starting point, and it doesn't matter if it's 0 or not because it depends on the scale of the variable. Okay. So let's get a variable in there. New model, picking up education, picking up another fixed effect. So it's beta 1 because education is the first predictor. If I had another predictor, what would its fixed effect be? Beta 2. And the next one? Beta 3. Yeah. So now, the only thing that has changed is the addition of this one word, education. So note, this is the uncentered model. I showed that prediction to you in the slides, and so I wanted to follow up with that. This is what you get. Education is added after the outcome in Stata. So one of the things I dislike about Stata's lack of things is that you have to just memorize that y comes first and that anything after is an x. Whereas at least SAS gives you a little bit of a clue with the equal sign. But that's just my own personal issues. Okay, so this variability, 1594, that's what's left. So this is the collection of offnesses from my sample after predicting income from education. Here's my new solution. So this set of numbers, more generally, is called the solution for fixed effects. Right now we have two fixed effects. We have the intercept and we have a slope for education. By the way, this out here, the beta 0, the beta 1, that's me being nice. SAS does not label your parameters or interpret them for you. If it did, I would be out of a job. So previously my fixed intercept was 39.7. It is now minus 52. What? Can you have minus 52 income? You could be that overdrawn, I suppose, but that's not what this study is about. What does minus 52 mean? That's my fixed intercept, which is defined as the expected outcome when the x's are 0. So look at what my predictor is. It's years of education in its original metric. So minus 52 is the expected income for what kind of person?
No education.
0.
0 education. Do I have anybody like that in my data set?
No, that's why you had to adjust.
That's why I got to adjust. So in the sense that you can pick any point on the line and the line goes on forever, this isn't wrong, but it's weird. The slope, the 6.6, that number doesn't care where education is centered. It's the slope is the slope. So these are the numbers that we just looked at in the output. But here's the plot then that shows what that model is telling us. I had to extend the range of the x-axis to get all the way out to 0 because that's where the negative 52 is. The slope of this line for every year of education, income goes up by $6.6 thousand. So let's fix it. Here's the difference. There we go. We'll play Where's Waldo? Can you spot the change? What's different about this equation?
You centered it by
Cent?
the minus 12.
Yeah, so when you write your equations to describe your model, it's helpful to describe the centering as part of the equation. That way people know what 0 means. Consequently, I've changed which predictor variable I put in. It's education 12. That's the new one that I made that is education minus 12. I also added some code to give me a lot of pictures. And so if you run this code, you'll see all kinds of pictures get spit out. I only kept 1 or 2. And this is the same code in Stata to try and get all of those pictures. So after centering education, same amount of variability left over, same slope for education, same significance. So that's why I say which constant you center around it can't be wrong. It's still the same model in the sense that it still captures the same amount of variability. It still generates the same predicted outcomes. The only thing that changes is the fixed intercept, the UR here sign, is now a different reference point. $27,000 is the expected income for what kind of person?
5 years of
12 years of education in this case. That's the middle of my data. So that's this plot. So does education matter in predicting income?
Yes.
We reject the null hypothesis of no relationship. Education matters. How does it matter? Does it help or does it hinder? Help, because you want more money, right? Not less. Usually more is better, up to at least to a point. So some pictures then. This plot was generated for me automatically, and this one is part of the extra plots diagnostics I asked for. This is a histogram of the residuals. So in other words, I asked it to predict income for each person in the data set using their education, and then to create the residual E for the difference between their real income and the predicted one, and I made a histogram of that E variable. This, my friends, is what should be normal. And I have the blue curve is what a normal distribution would look like if this was the mean and using the residual variance, and the red is one that's like more specific. It's trying to shape. So what do you think about that shape? Exactly. Yeah, it's not perfect, but it's not too far off. So that's the assumption that we're working with, is what's left after we're done with it is normal. There are whole chapters of textbooks that talk about data cleaning and data transformation. Have you heard of these things? Pretend you never did. Try to forget. Because data are not fish. They do not need to be cleaned. And cleaning data in the absence of a model makes no sense whatsoever. So it's residuals that matter, never what the original outcome looks like. Okay. So this number, 6. 6 is a lot, right? But I don't have an intuitive sense of is 6 good? Well, I know it's not 0, but that's not an effect size. That's an unstandardized estimate that depends on the scale of my variables. So one of the things that I can ask for is a standardized version of that. And that was in, let me find the equation for that. Here it is. A standardized version is the unstandardized fixed effect times the standard deviation for your x predictor divided by the standard deviation for your y predictor. So it functions kind of like Pearson's correlation in the sense that it removes the differences in scales and it puts a standardized coefficient on a Pearson correlation scale from -1 to +1. And lo and behold, I run a different procedure in SAS to get those values. STB, they show up in Stata by default. The standardized value is right here, 0.45. Have you seen that number before?
Yes.
Yeah, that is the Pearson correlation. So when all is said and done, this general linear model regressing income onto education is giving us the same information as if I had just correlated education and income. So why am I bothering?
Because this is like the empty one.
This is the next step past empty, but where else could I go with correlation? Like, that's the end, right? Where can I go with this?
Prediction.
Yeah, let's figure out what else matters. Does gender matter? Does race matter? Does age matter? Does blah, 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 right? So that's why we do models. It's to be able to incorporate multiple sources of prediction at the same time, make them compete, make them try and figure out what's redundant, what's not. But if you only have one predictor, then this is functionally the same thing as a Pearson's correlation. The story changes when you have more than one predictor, which is going to be next week. So, along with the binary predictor. Questions? All right, then let me know if you need homework help. Office hours in here later today at 3:15, and I will see you next week.